So, our brave heroes set out on their perilous journey, braving dangers like AP tests, English projects, and the greatest villain of all, procrastination. However, they were unable to find inspiration until one day when something happened.
Go!
Ow! Apple. Why did it fall?
The answer to that question is both because Makayla is evil and enjoys watching me suffer, and the other, as you should all know, gravity. But what is gravity? Gravity is the attraction between physical bodies dependent on their mass. On Earth, this means that the objects will fall towards it at roughly 9.8 meters per second squared, because it is many orders of magnitude larger than us. Of course, being the broad-thinking physics students that we are, this only left us with more questions. One, however, stood out. Go.
But what about big things?
My sadistic colleague is right. While knowing the Earth's freefall acceleration is useful, it's not very general and can only be used for objects on the surface. To find the force of attraction between any two objects, we would use the formula F equals g, the gravitational constant, times the masses over the radius squared. This works for any two objects, regardless of size. For example, the Earth has a mass of about 5.98 times 10 to the 24th kilograms, and a radius of 6.3 times 10 to the 6 meters, so it would exert a force of 9.8 newtons on a 1 kilogram object. If you're as smart as I think you are, you'll notice that 9.8 is also the freefall acceleration.
Yes.
While preparing her apple-based flail, Makayla began to swing it around at a faster and faster rate. Eventually it began to move fast enough so that the force exerted on the string was greater than it can structurally hold. The force acting toward the center of an object moving in a circular motion, like her apple flail, is called the centripetal force, and it was this force that broke the string. The direction of the object, in this case an apple, will always be perpendicular to the force. To solve for how fast the apple was traveling, we would use the equation v equals 2 pi r over t, the time it takes for a full revolution. The apple made a full revolution in 1.4 seconds, and the radius was around 2 feet. So the apple comes out to have a final velocity of about 8.97 meters per second. So okay, we thought, that's simple enough. But what about objects like the moon that continually orbit the Earth? How do we tell how fast they're going, or how high they are? Well, physics has an answer for that too. Any object in orbit around a planet or other celestial body orbits at a velocity equal to the radical of the planet's mass times the gravitational constant over the radius. Makayla here will show you an example or two. Makayla, is that a knife? Holy crap, what are you doing with the...
We all fall down. Now that the fun is out of the way, some people have been asking obnoxious questions like, when will we use this? Or how does this apply to us? Well, let me tell you, solving for orbits can save lives. Why, just last week, I was on the wonderful moon of Yavin 4, visiting my buddy, Luke, when out of nowhere this giant space station called the Death Sun, or something of that nature, shows up in orbit around the same planet Yavin is cruising around. Everyone there began panicking and crying, and all sorts of lovely things like that. None of them had any idea how long they had, or even how to find out, because fighting a rebellion hadn't left them much time to learn their physics. Luckily for them, I was there with my knowledge of the formula V equals the radical of the mass of Yavin multiplied by the gravitational constant over the distance. I was able to solve how long it would take the Empire to travel the 3.5 times 10 to the 7th meters to reach them. The answer came out to be exactly 15 minutes, which was strange, almost like it was a movie scene. Thanks to physics, I was able to let the rebels know how long they had and let them plan accordingly, defeating the Empire and saving the galaxy. There was also a lovely explosion. So I don't ever want to hear, "Where will we use this?" again. Ever.
Go.
Ow! The apple. Why did it fall?
Spin. Not spinning.